For the last couple videos, we've been studying measures. We saw their definition and a few examples. And now in this video, we're finally gonna study their properties. These two properties are very important and very easy to prove. So in this video, we're gonna study them a bit. First of all, we have a measure space. So we have that X is just any set that's non-empty. M is a sigma algebra. And mu is a measure, and obviously the measure mu is defined over the sigma algebra M. That is, mu is a function that grabs elements in the sigma algebra and gives them a positive number or zero. The first property is monotonicity. It says that if we have two sets and one is bigger than another one, so E is contained in F, then the measure of the smaller set is smaller than the measure of the bigger set. It just makes sense, right? If we have an interval and we have, let's say that this big interval, if this is F, and this smaller interval, that's a subset, this green portion is called E, then we would actually expect the length of E to be smaller than the length of F. Let's start proving this. So we're going to prove property number 1. Now, as we said, E is contained in F. So what this is telling us is that we can actually write F as E union F minus E. So let's remember what F minus B is with a Venn diagram. If we have two sets, A and B, we know that their intersection is this orange part and the union is everything. But what is A minus B? Well, it would be A and removing the intersection. So A minus B would be this portion here. We are removing this intersection and keeping all the elements that are only part of A. So in this case, we have that E is contained in F. So if this big set is F and the smaller set is E, then F minus E is just all this part removing the inner circle. But then to this, we are adding E. So we are adding this portion we just removed. So this is showing us that this union is disjoint. Okay, so we can actually write F as a disjoint union, and I'm gonna use this notation. E union with a D, just to mark that this is the union of disjoint sets. This is E union F minus E. But now the definition of a measure had that the measure of a union is equal to the sum of the measures. So then, because mu is a measure, and because this union is disjoint, then we have that mu of, in this case, F, is equal to mu of E plus the second term, mu of F minus E. So we can see that this mu of F comes from this term, mu of E comes from this term, and mu of the difference comes from this third term. But now the measures, as we said up here, gives us a positive number, or 0. So mu of F minus E is actually greater than or equal to 0. So in order to get the measure of F, we have to add a positive number to the measure of E. Well, this equation is just telling us that mu of E is smaller. It could be equal because this measure could be 0, the measure of the difference, but it's smaller than or equal to the measure of f. Because in order to reach it, in order to get this equal sign, we have to add to the measure of E a positive number. So that proves part A in this theorem. We have now monotonicity. Perfect. Now we have to prove subadditivity. Subadditivity says that we have a sequence of elements in the sigma algebra. Just any sequence. They could be disjoint or not. They could have some intersections, some disjoint. We don't care. Just grab any sequence in the sigma algebra. Then this happens. You get that the measure of the union is smaller than or equal to the sum of the measures. Now remember, from the definition of a measure, we know that if these sets were disjoint, then here we will have an equal sign. So this is actually generalizing that, and it's saying that whenever you grab any sequence, you'll have that the measure of the union is less than or equal to the sum of the measures. And this actually, again, it makes sense because we could be in a situation like this. Let's say that now we have this set here is F, and this other set is E. So the union of F and E has this measure. This is the measure of F union E. And the measure of F is this portion. The measure of E is this portion. So the measure of F plus E, again, this is the measure of E, the measure of F, the sum of the measures, so these two adding up, we will get the measure of F up to this point. Then we get from this point all this green line here, so we have this piece, and then we go to the measure of E, and again we have all this segment, so we add it, and then we have this final piece, so we just add it. And this white line would be the measure of F plus the measure of E. And we can see how the pink measure, the measure of the union, is indeed smaller to the measure of F plus the measure of E. So it makes sense, this property, but if F and E were disjoint, then we would just have the equal because mu is actually a measure. Okay, let's prove it. I'm gonna write it again, what we wanna prove. We have a sequence, E sub j, from j equals to 1 to infinity. It's a countable sequence in our sigma algebra. And we want to prove that the measure of the union is smaller than or equal to the sum of the measures. And what we're gonna do is, well, the only thing we know is that mu is a measure. So we have to use that to our advantage. Mu is a measure, so we know how to calculate the measure of unions of disjoint sets. So why don't we create a new sequence from this one? Let's create a new sequence that satisfies the definition of a measure, that satisfies that it's disjoint. So what we're gonna do is take one, the first element in a new sequence is gonna be the first element in your original one. Now when you want to create the second set in a new sequence, what you will do is grab the second element in your original sequence and subtract the first one. Okay, so F1 and F2 are two disjoint sets. Continue like this, so f3 will be the third element, and you will remove the second element and the first element. So then f3 is disjoint to f1 and is also disjoint to f2. So just continue this way. Eventually you will get an f sub n, for n a natural number, will be the nth element in your original sequence, but subtracting the union up to the last one of the elements in your original sequence. So now we have two things. Well, first of all, the new sequence is disjoint. And second, because each f is grabbing the corresponding t and removing something, then what we get is that for each n, f sub n is a subset of e sub n. Because we are taking e sub n and just removing a few things. And this happens for all n. So we have these two things. Now, the fact that f sub n is a subset of e sub n, using the first property we proved, we get that the measure of f sub n is smaller than or equal to the measure of e sub n. Okay, this is because we are using the first property. We have a set that's a subset of another one. Then the measure is smaller to this measure of the big one. So let's continue with the proof. We have these two properties for the new sequence of sets f sub j. Now another property is the union of f sub j's is equal to the union of the originals. Okay, so we have these three properties for our new sequence f sub n. Let's now calculate the measure we want. We want to calculate the measure of the union of e sub j. We want to prove that the measure of this union is smaller to the sum of the measures. But now, because of this property right here, we have that the measure of the union of the e sub j's is equal to the measure of the union of the new sequence f sub j. But now the sequence f sub j is disjoint. So because mu is a measure, we get that the measure of the union of disjoint sets is the sum of the measures. So this measure is equal to the sum of the measures of each f sub j. But now we have that the measure of f sub n is smaller to the measure of e sub n for every n. So then this is smaller than or equal to changing these measures for the measures of our original sets. And that's it. This is exactly what we were trying to prove. So we have finally finished our proof, and we can say that all measures satisfy these two properties.